Well, thank you very much for the invitation to be here. It's a pleasure. My sort of role in the NTD at the moment is I direct the London Centre for Neglected Tropical Disease Research, which is a collaboration between Imperial College, London School of Hygiene and Tropical Medicine, Royal Vet College, Natural History Museum, and interestingly the Sanger Centre in terms of their whole genome sequencing for parasitic infections. And our objectives are not advocacy or implementation. Our objectives are scientific research to improve understanding of how best to control infections. Now, what I'm going to do today, because of the timing, is I'm going to focus just on two questions. The first is more to do with mass drug administration and perhaps the need for some combination formulation for a drug. And then the second one is a new vaccine. I can't talk precisely about it because the paper is in press in a major journal, and therefore they're very fussy about advanced information concerning efficacy. But that is a schistosome vaccine, and I'll give you a rough outline of the problems and issues there. Now, when I joined GlaxoSmithKline's board 9 years ago, and when I arrived as a typical academic, I thought the difficult bit was innovation. It didn't take me very long to realize that the difficult bit is actually development, licensing and manufacture. And so at the end, I'm going to come back to those issues. I'm going to talk a little bit about detection of transmission and elimination. It's a word that's cropped up in WHO guidelines and jargon recently. And I just want to say that we've only done it twice in medical and veterinary science, and it's quite a difficult problem, and it's a very difficult problem to establish too. And it depends on spatial scale, obviously. Okay, start with the human helminths, because here we have successful MDA programs. It's quite interesting how WHO sets its guidelines here, quite sensibly, is it convenes committees. You have a consensus opinion among specialists from all sorts of different areas, different countries and so on, and you develop a set of guidelines for control, given the available options. In today's scientific world, if we were in engineering or physics, you wouldn't do this. You do optimization calculations to work out exactly what was the best way given your options. And encouragingly, we're now moving into an era where one can do this with real precision. We can look at low, medium, and high transmission settings as defined by WHO for whether it's filariasis, onchocerciasis, soil-transmitted helminths, or schistosomes. We can define the coverage levels, which would get prevalence down to very low levels. We can define who should you target treatment at in a quantitative, analytical way. We can look at breakpoints in transmission, in other words, is elimination possible? And we can also calculate how long you've got to keep going at this exercise. Now, if you're in the industry, this last point is rather important because, in essence, if you're donating these drugs, pharmaceutical company boards want to know how long is that going to go on for? What manufacturing capabilities do we need? How are we going to sustain those in a cost-effective way? Do we need to expand them or do we need to contract them? And those problems with albendazole, GSK is confronting right at this moment because the LF treatment program is scaling down, the STH, soil transmitted health program, is scaling up, but it's not quite clear yet what manufacturing capability is required. Now, epidemiology is essential to all this, and it sometimes gets forgotten. Here's a classic. 3 major soil-transmitted helminths, Ascaris, trichuris, and hookworm. These are the age prevalence and age intensity profiles typical for countries with endemic infection. And if you looked at Ascaris and trichuris, you say, well, targeting 5 to 10-year-olds and 10 to 20-year-olds would probably get most of the infection. If I look at hookworm, clearly, if I target the young, I'm not going to get most of the infection. I'm not going to treat most of the morbidity. It's pregnant women, hemoglobin counts, and so on that are really the major cause of morbidity for hookworm. And yet, WHO guidelines for morbidity control say target pre-SAC, which is preschool-age children, and school-age children. Now, there's no analysis required here. It's intuitively obvious. The only thing you have to do is to translate these profiles in a community or a country into how many kids in each of these sections, how many adults in these sections. So demography matters. Remember, our demography is like a flat square. If we survive the first few months of life, survival is very good up to about 70, and then it starts to plummet thereafter. In many poor countries, survival is exponential decay. Getting through to age 5 is rather important, and then it decays constantly and exponentially. So if we put demography on this, and here's one example, if we follow the school-age children treatment guidelines for hookworm, and here's Uganda as an example, by treating them, we would only treat about 15.7% or 16% of the worms. And that tells you something very important. Treatment will have to go on forever unless something else changes. And therefore, the manufacturing supply of this drug, albendazole and mebendazole, will have to go on forever. And it's a mute question whether the industry will continue funding these things on 10, 20, 30-year horizons. I hope they will, but we'll have to see. Drug efficacy is important, and the one I want you to focus on, this is a very good review paper from Swiss Tropical Medicine Institute. If you look at albendazole and mebendazole against tricuris, this is a meta-analysis of all the published information, and you can see that the cure rate is pretty low for tricuris for both mebendazole and albendazole. So what we're seeing in countries at the moment where you're stepping up MDA is that the hookworm and ascaris are vanishing and the tricuris is becoming dominant. It's rather like pneumococcal vaccines against conjugate vaccines against serotypes. The 1216 or 1213 that are in the vaccine, those serotypes are getting very rare. The others are becoming very, very common. And so tricuris is going to be a problem of the future. Now, essentially, the very odd thing about helminths, and it's true of all of them, is that unlike viruses, particularly, we have no strong acquired immunity to helminth infections. The reason for that biologically is well understood. Essentially, if you look at the tegment of helminth, you see lots of glands. They are secreting small cytokine-sized molecules. They're modulating the immune response. And so, in essence, when you treat a child and the child goes back to the community, in the absence of further treatment, the child will bounce back to the pre-controlled state. But if you get down to very low transmission, there is an unusual situation. Because these are dioecious species, in other words, separate sexes, there comes a stage where the prevalence and intensity is so low that you cross a reproductive threshold, where you cannot sustain transmission because the probability of being mated successfully drops to too low a level. It doesn't have to go to 0, it just drops below a level to sustain. And that's called the breakpoint in transmission. And Bill Gates has recently funded a program, DW3, cost of about $26 million, to test this concept in a big organized cluster randomized controlled trial in 3 different countries, 2 in Africa and 1 in Asia. And that's just starting at present. So everyone's going to try and find exactly where this breakpoint is. Now, technically and scientifically, we now have all sorts of tricks of the trade to estimate parameters from data. These use Bayesian and very sophisticated computational methods. So it's no longer sort of a guesswork exercise, this. You can estimate the parameters precisely for transmission intensity and so on in a defined locality. One of the most powerful methods is this MCMC method, which may be familiar to some of you. Then we can calculate breakpoint surfaces. This is hookworm. You've got 3 groups of people here, SAC, adults, and pre-SAC, preschool-age children. And you've got low, medium, and high transmission settings, and this tells you where this breakpoint is. And for hookworm, it shows you instantly that if you don't treat any adults, you're never going to stop transmission. Now, for ascaris and trichoris, it's a lot more complicated. These surfaces have lots of subtleties in them, but again, you can calculate them. And then you can do things where you can construct a table for the rounds of treatment versus the coverage levels, and what is the probability that you will break transmission if you've had N years of annual treatment at a given level of coverage. The green zone, you're going to break transmission. The pink and red zone, you're never going to get there. So turning opinion into calculation is absolutely possible today. Now, the real stumbling block here, and indeed in some other areas, as we're going to hear talks about the filarial worms, is, of course, drug efficacy. And I just wanted to end this bit before turning to the schistosome vaccines on two issues. Trying to detect elimination is a staggeringly interesting scientific problem, but quite a challenging one. So even if you design a randomized controlled clinical trial on multiple, the clusters could be groups of villages. When you've treated for a number of years in annual or biannual rounds, there will come a point where you think you've crossed the transmission breakpoint. But in statistical sense, the chance events play an important role. This point is that shaded pink oblong circle-y thing, and in the top graph, and in that zone you might begin to feel that you stop transmission. Now the interesting nonlinear dynamic here is in the blue line that you stop transmission after the third round with high coverage. And then it looks as though things are bouncing back. But actually that trajectory will eventually turn over with no further treatment and go to extinction. And so statistically you have to calculate two things, PPV and NPV. PPV is a positive predictive value. It's the prediction that this will go to extinction when it truly does. And the NPV, the negative predictive value, is that you predict extinction, but it doesn't go there. And the ideal situation for the design of a trial is to have the two distributions of these probabilities very separate. And you're trying to maximize both, actually. And one could do that today. And the new Bill Gates trial is designed along these lines. Now, the point I wanted to leave for the industry is in this slide, collaboration with Hugo Turner, who was a research fellow in my own group for some years. He's now at Oxford working on malaria. He's a health economist stroke epidemiologist. And this is looking at albendazole and ivermectin to deal with this forthcoming problem of the persistence of trichuris, because albendazole and mebendazole are poor quality drugs for that infection. And some preliminary trials, Joseph Veracruz, some of you may know, shows that this combination, if you look at the right-hand side of the bars, is annual targeted, this is pre-SAC, ineligible for ivermectin, as many of you clinicians will know. But in essence, the heavy case years averted in an economic analysis are dramatically improved by using ivermectin and albendazole. Not hugely, I mean, this is not a step jump, but it's a much, much better. So the pharmaceutical problem here is, can you co-formulate? And of course, in the industry today, both with TB and with HIV, there's a lot of experience about co-formulating drugs. That's not the technical problem, is not the dominant problem. The problem actually is much more to do with licensing and clinical trials. So we're at an interesting stage with MDA. Scientifically, we can say precisely how to do it. You no longer have to rely on opinion. We still have some problems with these drugs, and we have problems in detection of elimination. That's very true with STH, but it's equally true with LF and onco. We don't know whether this magical figure of 1% prevalence is a true estimate, or if you get down to there and you stop something, and you give another 5 years, the whole system is going to bounce back. We don't know that. So it says that phase 4 in a clinical trial design is very, very important to monitor carefully what happens when you stop treatment. I should just comment on schistosomes and praziquantel. Schistosomes are somewhat easier to deal with, and when you look at the WHO guidelines and you look at the treatment, as most of you know, that most of the schistosomes are in the school-age children. There are some settings where they're not. I can think of settings in Kenya where you've got infection going into late teenage and adult age classes. And clearly your design of a program needs to be focused more on the epidemiological setting. But in high transmission settings, the current strategy of WHO will never work. You've got to extend treatment to the adult age groups. And again, with schistosomes, you can do calculations. We shouldn't have to rely on opinion. This field is much more opinion-related than actual calculation-related. And also there's an interesting pharmaceutical issue here. Is it worth having a formulation of praziquantel for PrESAC, for young children, infants? And the answer epidemiologically is no. But the answer for the individual is probably yes, because you're preventing that child having morbidity going into the future. But epidemiologically, it adds nothing. You get much more by treating adults. I'm going to skip this. Let's turn to the vaccines. This is the point I want to end on. Now, 3 years ago, I was asked by the Gates Foundation in confidence to evaluate what was potentially a low-efficacy vaccine for Schistosomal Manselli. About to go into baboons, the work being done by Afzal Siddiqui in Texas with his research group funded by the Gates and NIH. And they said, basically, we want to know how good is good enough in terms of this vaccine. And they said, how do you think it might act? And of course, with a macroparasite, a big worm, it can act in 3 ways. It can reduce establishment, it can reduce life expectancy of established worms, and it can reduce fecundity, or all 3 to some degree. So then we helped Afzal think about experimental design and what to measure in these baboons. Baboons are expensive, $10,000 plus per animal. And so if you're going to do a trial which involves multiple groups, multiple adjuvants, and you're going to look over a period of, say, 2 years, this is a very, very expensive trial. Now, 2 trials have been done, and the results of the second one are now known. They're unblinded, but I can't talk about the precision as yet until they're published. So what we did was say, given the measured activity on establishment, adult worm survival and fecundity, in a cohort immunization program, what would you have to achieve with the vaccine? And we made this following assumption, which I think will be true. For schistosome infections, which modulate the human immune system, if you vaccinate an adult who's got past experience of infection, the probability of an adverse reaction to that vaccine is probably very high. Don't know. Have first into humans in a transmission setting will be required to do that. Now, these are 2 calculations here. Intensity of transmission, which is the R0 value on the bottom, going from 1 up to 10. An efficacy of vaccine, 5 is high transmission, 2 is medium. And the efficacy of the vaccine, and here we've concentrated on reducing establishment, which is the best outcome if you've got it. The vaccine does actually operate on all 3 of the parameters I've measured, but its biggest effect is on the one here, the efficacy of establishment. So that's important. And if the efficacy is very high, you can get away with cohort immunization of infants at a level that's, perhaps somewhere around, a lowish level, 60%, which isn't a typical MMR program when started in Africa, had that sort of coverage, measles, mumps, rubella. So we know through Gavi that's achievable. Now, the big unknown in all of this is the duration of vaccine protection. And quite correctly, there's an ethical issue with doing experiments on primates where if you infect an animal, you cannot leave that animal too long without treating or autopsy. So to leave a baboon infected with Schistosomal Manselli for 2, 5, or 10 years under current regulations in the United States and Western Europe would not be acceptable. So duration of protection may have to be done in humans in field settings, rather like the dengue and the malaria vaccine, the falciparum vaccine. So duration of protection matters hugely, and it really would complicate. If it's very short, you've got a problem. It doesn't have to be infinitely long. It can be somewhere of the order of 20 years, and you're in a moderately good place with cohort immunization in a high turnover population. There are a lot of elegant scientific things in these calculations which can be extracted. This work is in press. The lead person is a postdoc with me, Andrew Stiliano, and James Truscott, another postdoc. And this is in press at the moment, this paper. So here's the duration of protection. If the duration is only 1 year, you've got to vaccinate 99% of every cohort going into the population. If you're at 50, 20 to 50, you're getting into more reasonable domains. 20, just about doable. You get 91% in Western Europe with childhood vaccines, but that might be challenging in Africa. So you'd prefer something that's a lot longer. Now to end. Transmission elimination, I've already summarized. You can do calculations, you can do it. There are major problems in compliance and adherence. Compliance meaning the percentage coverage reported by WHO. WHO knows this, so I'm not being disloyal because they're a wonderful organization, but many of the figures published by countries are a bit fantasy, really. The coverages are much higher than those in practice achieved. Adherence worries me even more because if you're saying you're treating 75% every year, if it's the same 75% each year, you've got a problem. Because in the 25% you're not getting, the infection is sustained transmission-wise. So the longitudinal adherence, which is never measured in any of these MDA programs, is crucial. So we know how to do this, and it's the practicalities of achieving it. And it would be nice to have another drug for trichuris. The vaccine business, I think of this. The dengue vaccine took 20 years to the current point in time when we've got licensure and big trials of a phase 4 nature going on or about to start in South America and Southeast Asia. The malaria vaccine took 30 years from discovery to the present point. Neither of those two vaccines would have got to the present point unless Bill Gates hadn't made a very substantial contribution to phase 3 trials. The average time from discovery to market for a vaccine now is about 8 years. The average cost in Western societies is of the order of $600 million plus, and a very significant fraction of that lies in phase 3 trials. And the reason for that is our obsession, correctly, with safety. So if a new vaccine, such as the shingles vaccine, has a case complication rate of between 1 in 200,000 or 1 in 300,000 people, it's dead. It really is dead. So you're not really going to get that through FDA into market. So the first thing for the Ebola vaccine or a Zika virus vaccine or indeed a schistosome vaccine is, can we change our obsession with safety and pay off the population balance between saving morbidity and saving lives versus a few people? Remember, the most variable bit of the human genome is our HLA and IR gene background. We're all different how we react to vaccines. So that's the first thing. The second thing is, do we have an economic or financial model? I should just say the schistosome vaccine, although I can't mention the real figures, is fantastically exciting. If it was for an infection in children in Western Europe, North America, a company, one of the big three, will be piling ahead with it. It'll be first into humans, into phase 2, into phase 3, provided nothing funny happened. Now, this is a vaccine that there is no rational financial model for producing. So you've got to go first into humans. Let's say that's 20 million or 30 million, perhaps more. Probably a foundation will fund that. The next stage, phase 2, is not too expensive. It's the phase 3 I'm worried about, because there you've got infected communities and you've got a lot of people with quite strong immunological responses to Schistosoma mannsoni antigens. So the probability of an adverse event is going to be high. And so I end with just leaving the thought in your mind that our problems are not now scientific discovery so much. They are thinking of a financial and economic model which will take some of these NTD vaccines from discovery through trial into market. Thank you very much for your attention.